Throughout the course, we've gotten a good look at how to solve differential equations. We looked at first order differential equations, and we learned about how to use separation of variables and integrate. We learned other various methods for working with first order differential equations. We then looked at higher order differential equations, in particular linear second order differential equations. We saw that for homogeneous equations with constant coefficients, we could use the auxiliary equation. Even for non-homogeneous higher order linear differential equations, we learned about how to solve those using undetermined coefficients, for example. And we even developed the method of variation of parameters, which allowed us to take the complementary function, or the solution to the associated homogeneous equation, and build a particular solution out of those. Now, despite going through all of these different analytical approaches to solving differential equations, not all differential equations, in fact many of them, will not be solvable in terms of elementary functions. Okay, in terms of the functions that we know, to basically write a solution in closed form. The elementary functions, of course, are like the exponential, the sines and cosines, the different trigonometric functions, polynomials, rational functions, and so on. So a very powerful tool in our arsenal for dealing with differential equations, in particular those with variable coefficients. Okay, so those could get quite complicated even when they're linear. Okay, a powerful tool is to use power series. Okay, no pun intended on that one. In any case, using power series to solve differential equations is an essential part of it, part of solving differential equations, and it's indispensable. Okay, this topic is extremely important, and if you're working with differential equations, you're going to go through power series of them, whether you're approximating terms in the differential equation or plugging in solutions as power series. You're going to be dealing with power series if you are working with differential equations towards concrete applications in physics, engineering, in mathematical modeling, anywhere where differential equations show up. And so the purpose of this video will be to review some of the basic properties of power series. We're not going to go in depth. This is just a pure review, very quick. For those who are interested in going more in depth into power series and series more generally, I strongly encourage you to watch the videos I have in the Calculus 2 series that deal with series and their convergence. We also look at power series there and different applications. So I strongly encourage you to watch those videos towards the end of that series of Calculus 2. So let's get started with our review. So power series, centered at A, the point A, has this following form. This is what a power series is. And what's unique about power series is this infinity there. That's really important, okay? So that's what distinguishes a power series from just, say, a polynomial of nth degree, is you have this infinity. You're summing an infinite amount of terms that look like this. This here is the nth coefficient to the term x minus a to the nth power, okay? So these are called the coefficients, and the center, notice the center shows up as this kind of shift of the variable that we're looking at, x. So that's what power series are. The infinite part there is very important to the definition. You could somewhat think about it as an infinite polynomial, although, you know, here's what it is. So let's talk about the convergence. A power series converges at a point x if the sequence of partial sums, Okay, this S sub n, this is seen as a set where each element of that set is S sub some number, okay, is equal to this. Okay, so this is just the sum of n plus 1 terms, including the 0, okay, where n is this capital N. So you're summing these n plus 1 terms. That's finite. Nothing wrong with that, right? Of course, any finite sum will converge. Now, what about the power series? Well, what we do is this limit. Okay, this limiting process is really important. So we could sum to an arbitrary capital N and then take the limit as that capital N goes to infinity. And if that limit exists, we say that the power series converges. If the limit doesn't exist at a particular point x, and of course here we're looking at the point x, which of course could be extended to a set. But if that limit doesn't converge at a point, then we say the power series diverges and is divergent. Okay, if it converges, it's convergent. Where the power series converges is not this, is very important. Okay, so we have this concept called the interval of convergence. So, we can't just say a power series converges. Well, where, right? And so the interval of convergence is the set for all real numbers x for which the power series converges. Okay? The center of the interval of convergence, okay? This looks like a typo. The center of, so mark that out, of the interval of convergence is the center A of the power series. Okay, so this here is going to be the center of that interval, and someone might think, well, why is it the center? How do we know that this point will lie right in the middle? Well, because that's just how they work. Okay, so you have a radius of convergence, so there's somewhat of a symmetry there from the center for how far you could go to the left or right of that point A, that center. Okay. The radius r of the interval of convergence of a power series is called the radius of convergence. Thus, with r strictly greater than 0, so strictly positive, and the power series converges for x minus a less than r. Okay. So that's what the radius of convergence is telling us, is that for any point x, such that x minus a is strictly less than r, then the power series will converge. Another way of saying that is if x lies between these two, then the power series converges. Okay? And diverges if it's beyond, strictly beyond that set. The radius of a convergence can be 0. That just means that the interval of convergence is the point A, the center. I mean, you could just plug in A into this, and you just get us infinite sum of 0 terms. Okay, so A always, the point x equals A is always in the interval of convergence, and if only that point, if the power series only converges for that, then r equals 0. And r equals infinity if x could be anywhere on the real line. Okay, and you would get this interval of convergence. Okay. Now, something to pay attention to, and why the interval of convergence is not exactly symmetric about the center, is because the power series may converge or diverge at the endpoints. Okay, so notice here, these were all strict inequalities. Okay, what happens at the point a minus r or a plus r? We have to probe that. You could get convergence at both of them. You could get divergence at both of them. So the interval of convergence could look something like, this. It could look something like this, where neither of the endpoints converges. It could look something like this, where only you get convergence at the right endpoint, or you could get convergence at both. Okay, and of course The square brackets mean that we include the endpoints. Okay, so that's something to pay attention to. Another here useful definition is absolute convergence. Definition slash statement, okay? In the interior of its interval of convergence, so outside of the endpoints, a power series converges absolutely. Okay, so we could say that about all power series. Again, endpoints is a special case we have to probe. That is, for x in this, then we're guaranteed that not only will the power series converge, but it converges absolutely. It's the absolute value of the terms converges, and that's a stronger statement than just convergence. We also have the ratio test, which will come in handy for Cn not equal to 0 for all n in this power series. Okay. Suppose that the limit as n goes to infinity of this. What is this? This is the n plus first term in the power series. This is the nth term in the power series. So if you take the ratio of the n plus first term and you divide it by the nth term, okay, including these, so it's not just the coefficients, and you take the absolute value of that, and you take this limit to as n goes to infinity, so you're looking at the ratios of these really far out terms, you'll get this L, which we just leave as L for this statement. If L is strictly less than 1, the series converges absolutely, okay, by the ratio test. If L is strictly greater than 1, the series diverges, okay? So this would diverge in that case. And if L equals 1, the test is inconclusive. And now someone could say, well, you're saying converges, diverges, for what x, right? Because x is a variable. Well, that's the whole point, okay? So we're going to see that for some x's, we get that L would be strictly less than 1. For other ones, we get that L is strictly greater than 1. For some of them, we get L is equal to 1, and the test is inconclusive. And so let's actually look at an example to see how we could use this. So here we have the power series, okay, and we want to find the interval and radius of convergence of it. What do? We use the ratio test, the n plus first term over the nth term, the absolute value, take the limit. Okay, so here goes the n plus first term. Just notice we just take n plus 1 there, and we divide it by the nth term, and we take the limit as n goes to infinity, and using just simplifying, we get these terms here. You could see that we could take out, just using the properties of exponential, we could take out a 2n there, so we could get to cancel those. We could take out an x minus 3 from one of these, and we get cancellations with the n values. And the limit as n goes to infinity of this is 1. This is just constant. Well, x is a variable, true, but for the limit, which is dependent on n, x is just treated as a constant. So we could actually take it right out of the limit, and we get just this left inside the limit, and this is 1, okay? And so we end up getting this term here. Now, if any of these manipulations were confusing, I strongly encourage you to review the Calculus 2 series on series, okay, or power series, to see how we computed them. Thus, the series converges whenever we get absolute convergence, whenever this thing, L, right, this is going to be our L, is strictly less than 1. Well, that occurs when x minus 3 is strictly less than 2. So right off the bat, we know then the radius of convergence is going to be 2 there, okay? That's just how, that's giving us half of the interval of convergence. Now, we also have to check the endpoints, 3 minus 2 and 3 plus 2. Okay, for 3 minus 2, x equals 1, and so we just plug in 1 in here, and we get this alternating term, okay? Now, it turns out this actually converges by the alternating series test, because these terms go to 0 and we have alternating series, and so we do get convergence again. This is just a review, but if you want to learn more about alternating series, that's in the Calc 2 series. And this endpoint, we plug in 5 into here, so get this 2 to the end there, and we then are left with this. And this is the harmonic series, and it's a common example in Calc 2. It diverges by the integral test. Okay, so the interval of convergence then is going to be this. We include the 1 endpoint. We don't include the 5 endpoint. Okay, and the radius of convergence is 2. All right, so let's talk about the relationship between power series and functions. Okay. The power series, in and of itself, defines a function, okay? With its domain being the interval of convergence, of course. Otherwise, you would get divergences, and f can't be defined equal to infinity, right? So the power series itself is a function. If r is strictly greater than 0, r equals infinity, then the function defined by this power series is continuous, differentiable, and integrable. Okay, when r is strictly positive or infinity in the interior. Okay, not at the endpoints, but in the interior, not at the endpoints generally. Those have to be probed independently. And f prime and the integral of f may be found term by term. What do we mean by that? Well, let y equal this power series. Then what this is telling us is that we could go term by term. If we want the derivative of y, we could take the derivative of each term. Now, if you just apply the derivative, you have to be careful, especially at the first terms when you're applying the derivative, because the first term, is x to the power 0, and so it's a constant. It's going to be 0, okay? Now, technically, this would cover this case, okay, but we could just shift the index there to ignore that trivial, to account for that first term just going to, the derivative going to 0. And we use the power rule. So if you take the derivative of x to the n, you get n times x to the n minus 1. So you get these terms. You could also do this term by, with this expansion, and you would get this when you take the derivative. Now take the derivative of that again for y double prime, which is what we're going to be using a lot, and you get a similar expression. I write here, notice the shift in summation index. This starts at 1, this starts at 2. And again, this is because the first terms, when you take the derivative of this, that's 0, and so it just doesn't even show up for the derivative. And when you take the derivative of this, that first term is going to be 0, and so it doesn't even show up. And so that's important to pay attention to. Identity property, okay? So this is super important. One could think about expressing 0, the function 0. So for any x equals 0, one could easily think about the power series for that is one with all the coefficients being 0, right? But what about the reverse? What if you find that for a given power series, it equals 0 everywhere? Now, can you go reverse and say something about the coefficients of it? It's not a trivial question, okay? You could imagine cancellations within these terms that, although they're non-zero, you get some cancellations and get 0 at the end. So it's not a trivial question. But it turns out that with the radius of convergence being positive, if you do have this, then you know that all these coefficients have to be 0, okay? Now, something I want to make infinitely clear here, okay? What's 0 is what's multiplying these terms, okay? Because when we're working with these, we're going to end up getting terms that multiply the power of x term, okay? So we're going to get terms that multiply the power of x, and we have this relation equal to 0. And all that means is that whatever is multiplying is equal to 0. Now that term will end up being some or linear combination of the coefficients. Doesn't mean that those coefficients are 0, okay? What we mean by coefficient here is anything that multiplies the power term, okay? Those things are 0. And here, in the very simple way that we're writing it, it will be Cn. And we'll see more when we get to an example of what I mean by the other thing. I'm just kind of throwing that out there as something to pay attention to. All right, so we know that the power series itself gives a function, but what about the reverse? What about taking a function and expressing it as a power series? How does that work? Okay, well, we know that functions have Taylor series, okay? And Taylor series are basically this expansion where, you know, you're getting a power series, okay? Now, I don't write equals here because, you know, again, go to the Calc 2 videos if you're interested in this, but even if the Taylor series converges, it doesn't mean it converges to the function, and so, you know, but on the other hand, for a given function, there is an associated Taylor series, okay? Now, what about those functions which can be expressed as a power series, okay? We give those a special name. A function f is said to be analytic at a point A, okay, if it can be represented by a power series in x minus a with r being strictly greater than 0 or r equal infinity, okay? So those functions that can be expressed as a power series are important, and we call them analytic. We give them a special name. And notice that this analytic property is defined at a point, and of course could be extended to an interval. But in general, you shouldn't expect that any function could be expressed as a power series at a point, saying nothing there of the power series then expressing the function on the whole real line or wherever the domain of that function is without the power series. So, of course, you'll recall that there is a special Taylor series called the Maclaurin series, and that's just when the center is equal to 0, okay? So Maclaurin series is Taylor series with center equal to 0. And here goes the Maclaurin series for some common functions. The exponential has this Maclaurin series, and it converges from minus infinity to infinity. Here you see the cosine, sine, arctan, cosh, sinh, natural log of 1 plus x, okay? And notice here with the arctan and the natural log and this 1 over 1 minus x, which gives you the geometric series in x, we don't get infinite convergence, okay? So this Maclaurin series will only work for this interval of convergence, okay? Now, from those Maclaurin series, we could actually get Maclaurin series of other things. So, for example, say you wanted the Maclaurin series of e to the x squared. Well, you could use composition, okay, and replace the x with g of x. Here, g of x would equal x squared, okay? And so if we want e to the x squared, what we could do is go to e to the x, and wherever we see an x, just substitute x squared. If it was g of x, we would just put g of x wherever we see an x. We'll make that substitution. And we end up getting this. The interval of convergence here is still minus infinity to infinity. You have to be careful when you're composing or summing or taking products, okay? the interval of convergence can change for these operations. For example, here, if you want natural log of x, well, we have natural log of 1 plus x, the Maclaurin series for it. But natural log of x is equal to the natural log of 1 plus x minus 1, okay? And so this is like taking x minus 1 and substituting in for x, okay? And we get the corresponding power series there. And something to note here is that we've shifted the interval of convergence in this case. Now it's 0 to 2, okay, rather than this minus 1 to 1, okay? And so here we also see how the interval of convergence can change with the composition. So you got to be mindful of that. Now we could do arithmetic on power series. Power series may be combined through operations of addition, multiplication, division. And let's just look at a concrete example here rather than just doing this kind of general theory. So we have EX sine x, okay? EX has this Maclaurin series. Sine x has this Maclaurin series. And if we want the Maclaurin series of e to the x sine x, well, here's an idea. Take both and multiply them together. Okay, you do that term by term. So for example, here's 1x and you get that. Okay, for x squared, you'll take this term and this term. Okay, and you'll get that. For x cubed, on the other hand, you'll have this term multiplying the 1, and there goes where that's coming from. And you'll also get this term multiplying this, and so you'll get that 1/2. And you could do this in combined terms, and you get this power series for it. Okay, and it turns out the interval of convergence here stays minus infinity to infinity. E to the x converges around that, sine of x converges on that interval. And this product will as well, though caution should be exercised with the issue of convergence after operations. So something that we're going to be doing, especially when we're adding power series together, is shifting the summation index, okay, or re-indexing. We saw when we took a derivative, the summation index shifted. Well, we could do this, and it's an important operation. So we have this power series there. Okay, we want to express it as one power series rather than a combination of two. Well, we're going to run into a problem. The first problem to note here, okay, and of course pay attention to where these start, is n equals 0. The first term is n equals 0. For this one, giving that the first term is proportional to x. X to the 0 plus 1 is just x. The first term here is x to the power 0, or you'll get a constant term. So you can't just naively just, add these together. You have to make sure. So when you add two power series together, you add them when you add the coefficients of the same power, okay? So just like we did up here, we got two different terms with x cubed from doing this product, and we combined the coefficients of those x cubed to get that. So we're doing the same thing here with these. Okay, so we have to add the coefficients of the same power of x. So since this first one starts at x equal x to the power 0, okay, it's just constant, and this second one starts with x to the power 1, we're going to get rid of the first term of this power series. Okay, so this is n equals 2. We're going to get rid of that n equals 2 term. Here it is. We took it out. And now we have these two. Okay, now what's special about these two is although their index starts at different terms, right, 3 and 0, the power of x is the same, and that's what we want. Okay? And now the rest is cosmetic. Okay, so both series start with the same power x to the 1 now. For first series, we're going to choose to associate k with n minus 2. Okay? Because we now want to have we want to shift these to starting with the same k. Okay? Also, so the major deal here is making sure they start with the same power, but we also want the same. We want to start at the same place. Okay? In terms of the index, so we could combine the indices together. So we're going to associate for the first series this one, k with n minus 2. And so n equals 3 is the first term. And so that would mean if we plug in 3 in this relation, we get k is equal to 3 minus 2, or 1. So we get to start this at 1. And we make the substitution. So if you solve for n, you move this minus 2 to the other side, you get that, make the substitution n going to k plus 2. Okay? And for the second series, okay, we are going to also want to shift this first term to be k. That's what we did for the first series, basically shift this to be k, and we want to shift that to be k. And so we're going to associate n plus 1 with k, and the first term is 0, and you plug in 0 in here, you get k equals 1. So that's the first term. And solve for n here to make, so the substitution, and you get the n, you must substitute for n, k minus 1. So we have this, that's what we start with. Okay? We get rid of that first term, so we have same power. Okay, that's that. And now we what do we do? Well, we take n, for this first one, we take n, and we make the substitution k plus 2. So here you see k plus 2, k plus 2. Put k plus 2 into n here, you get k plus 1. Okay? Because that 1 subtracts one of the 2's. Right? And so you get that. Instead of n, you get k plus 2. And you have an x to the k because of what you did here. Okay? Sorry, what you did here. Substituting k equal to n minus 2. I mean, this is how we got the relation k. So we do the same thing with the second one. Okay, here now it's k minus 1, and so instead of n, you get a k minus 1, and instead of n plus 1, you get k for that second one. And someone could say, like, did we have to use the same k? K is a dummy variable, okay? You could have used like L if you want, but at the end of the day, here's what we want. We want to add terms, with the same power of x, and we want these to start at the same place. Okay, that's how we could add the coefficients, all right? And now we can combine, because the sum is the same now. Okay, so we could, if you will, factor that sum out. They're starting at the same place. And now we could just factor out the xk because they're the same power. Okay, that's why we did all that we did. And we're left now with this. This is one power series. Okay? And you could see here that although the coefficients, like you could see k, the coefficients here is actually this whole term. Okay, this is what we mean by the coefficient. So be careful. Sometimes I'll use coefficient to just mean good old-fashioned c sub k, and sometimes I mean coefficient in the sense of coefficient of the x to the power k, whatever that is, okay? Which here is not ck, it's this, okay?